we have this idea of a machine having, or a network card or Wi-Fi card, having a MAC address, which I understand to be a unique address to that not necessarily that device, but certainly to that network interface, is that's probably the best word for it, is it? So the question is, why do we need IP addresses if we've got MAC addresses?
Okay, so it's an interesting question. It's because they do different things, I'd say is probably the glib answer to it. A MAC address looks something like 6 bytes would be an Ethernet MAC address. There are some details about the first few bits at the start of this, which can be used to indicate things like this is multicast and a couple broadcast and a couple of other things. And then you've essentially got, these indicate what you can think of it as the manufacturer. So you apply to the standards body, I think it's the IEEE, to get a block. You pay them some money and you get a block, and then you can mint your own MAC addresses from that. And then these would refer normally to the station on the network, on Ethernet. So that gives you a fairly big address space. You can address quite a lot in 6 bytes. So it used to be the case that these were burnt into the hardware of the Ethernet card back in the day when it was all, physical things and physical wires. There'd be something on the card which had this hard coded into it in the hardware. Nowadays, I mean for several years, particularly with Wi-Fi, it's been possible to set this through software in many cases. So you can't in fact guarantee there's a one-to-one mapping between the network card, which is used to be what it identified, and the MAC address for it. So you can change the MAC address on a given network card, particularly in Wi-Fi, which is one of the reasons why spoofing on Wi-Fi is actually easier than people think. Some people think. On the other hand, an IP address, it's a 4-byte number. In hex, that might be something like that. I'm not going to try and translate that to decimal in my head. An example of a decimal one would be 10.0.0.1. So that's a dotted quad notation. These are bytes. Each of these goes from 0 to 255. When you have Hollywood doing films, the number of times that CSI is a particular example of this as well, the number of times that people will do trace routes and other such things to IP addresses that start 700 and something. It's completely meaningless.
A bit like the Hollywood phone numbers 555 though.
Yeah, possibly. Maybe it's been done deliberately. It would be nice to think it was done deliberately. So you've got these 2 different address formats, and they're doing 2 different things. So this would be used to identify the frames for you on the Ethernet that you were physically connected to. So for example, on the Ethernet frame, this is why you start out with the destination address, then you have the source address, and then you have a protocol field. And it's because the first bits that hit the interface card should be the destination address, because the card needs to make a decision, should I receive this or not? Or should I just start ignoring it?
So this is a card sitting there on what is effectively an open phone line, and it has to know if this conversation is to do with...
Yeah, when you go back to the first versions of the Ethernet, you'd have Ethernet cards sitting on an Ethernet. They were called vampire taps coming off them. I think that was the first version of this. And then you'd have a much thicker cable connecting them. And it was called a vampire tap because literally you screwed it into the coax, it broke through the sheath and hit the core in the middle. And that was what connected the card to the cable. So you'd have multiple stations electrically connected to the same physical line. And so there'd be signals passing up and down this line. And each station needs to know, should I listen to this signal or not? Do I need to start receiving it, turning it into bits, passing up to the computer, into the memory, etc. You want to make that decision early, because back in the day, things were expensive and things were slow. So you put the destination bits first, and then the card can make a decision very early. Do I need to keep listening and put this into memory, or can I just ignore it? And it kind of carries through into technology today, even though it doesn't matter so much. If you look at an IP address, then the first fields, well, actually the first fields you've got a version, you've got a header length and such like. But the first fields in address terms, you get the source and then destination, interestingly. So it's the other way around, because by the time you got to this stage, it's maybe a bit less important, and you're going to have to do quite a lot more thinking anyway about the thing, about the packet coming in, so you don't need to make this very fast decision to decide to ignore it. The other thing about IP addresses is, so Ethernet starts out with the idea that you've got a bunch of stations attached to a particular cable. IP is with the idea that you've got multiple networks with different things in them, maybe different technologies, and you want to start interconnecting between these networks. So it's a much bigger thing to start with. You're trying to build a much bigger network than you're thinking about when you're building an Ethernet, where you've got generally things quite local. So this is known as a local area network, a LAN. Nowadays you'd think of different sizes of this. So you might think of a metropolitan area network or a MAN. You might think of a wide area network or a WAN, but it's a much bigger network. And so you've got a lot more information in some sense to encode. If you try using MAC addresses, they have no structure other than this manufacturer and this station ID. And so if you want to look up what to do when you've got got an Ethernet frame that's arrived and where you should send it, you just need a big table of everything, which on the internet is completely infeasible. Right? That's far too big, you've got no structure to it. With an IP address, you can do prefix matching, so you can represent blocks of IP addresses with a single entry. So you no longer have to have a table with 2 to the 32, about 4 billion entries in it. To make a decision what to do, you match it against the entries that you've got, which cover ranges. And so because it's got more structure embedded in it, you can sort of compress that information and you can make that lookup process quicker and you can help it to scale out more. And that's why IPv4 has this ability to do this global network, whereas it would be quite difficult to run a really global Ethernet just relying on standard Ethernet style protocols to do that. It wouldn't work so well. And that's why then IPv6 then has, one of the reasons it's got this bigger address space. So it's got 128 bits per address rather than 32 bits per address. It gives you more addresses. But then you have this ability, because they're structured, you've got this ability to compress them down, so you don't have to have 2 to the 128 entries in each IPv6 router, because that's a lot.
So the IP address is a bit more like a street address, okay? You can break it down into city, street, number, whereas a MAC address might be more like the phone number for that house. It would be hard to find that house from a phone number, and therefore just having a huge list of phone numbers is really not useful.
Yeah, the analogy's not that far away, I think. And it's certainly the idea that you've got structure in the address, and structure that allows you to compress the entries and allows you to make decisions from far away as well. So commonly in an IP network, some of these routers will have a complete table. So they'll have, I think currently we're running at about just something over 500,000 entries in that table, even given the fact that you can compress these down and express ranges rather than having to express each address individually. But some of these routers, particularly if they're routers in the middle of a network, may not, for whatever reason. So they may have default routes, for example. So it may be the case that you've got 200,000 entries, and then you've got one entry which covers everything else. And so that's the default route. If you're on a smaller network that's connected to a much bigger backbone network, quite commonly you'll end up with, you've got some addresses for the things that are inside your network and the things your customers connected directly to you. And then you might have a default route which says everything else that's not one of your own customers goes up to whoever provides you with service. And so you can sometimes have interesting cases where if, for example, this smaller network is multi-homed, as they call it, so it's connected to multiple bigger networks, and a mistake happens in the configuration, you end up being used as a through route for some reason. And this is then, well, it's not good for you because you're now carrying probably a lot more traffic than you can cope with, and it's not good for anybody else who's connecting to these two large networks, because now their traffic is taking this completely unnecessary hop, going further than it needs to, taking longer than it needs to get there, perhaps going through a bottleneck, getting slowed down to get there. So it's generally, it's a bad thing.
Sat-nav sending HDVs through a
Exactly, yeah.
Through a street, yeah.
And if you make a mistake, that route suddenly becomes visible to the sat-nav, right? And then suddenly all the HDVs go, oh, it's really fast to go that way. It looks like it should be really fast to go that way. And in practice it won't be, because now they're all piled in.
So what have I done? I've done a sorting of the data, and the approach I've done is something based on similarity measures.
Document 4 has 18 mice and 5 horses, and document 5 is only about the word mine, not about horses. And so the first thing you would do